Hello students, so in this lecture we are going to discuss about a very important material called silicon carbon nitride, or in short SiCN. Now the importance or the interesting fact about SiCN is it is a ternary compound. So if we look into the phase diagram of silicon carbon and nitride, we have N have carbon here, and if we put silicon here, the phases formed are Si3 and 4 and silicon carbide here. We have very two important phases. Now apart from that, sorry, this is not there. This is where silicon carbide is SiC. Apart from this, a very important phase called carbon nitride can form here. Now beta carbon nitride is a very hard material. Its hardness is close to that of diamond, and very stable material as well. But the stability of beta carbon nitride is always not possible. So we find different routes to create this beta carbon nitride. Now there is some way this beta carbon nitride phase can exist in this silicon carbon nitride phase. So due to this hardness and due to the thermal stability, this silicon carbon nitride material is extremely important. Now, before we can deposit silicon carbon nitride, we can have silicon nitride in the bulk form. So if we look into the bulk synthesis, then it is derived. It has got a polymer precursor route. And the main advantage of using a polymer pre-ceramic material is the possibility of obtaining various shapes. You can have various shapes, and it is mainly derived from a derived polymer called polysilazine. Now, as previously told, precursor derived SiC and ceramics are promising material for high temperature applications, and depending upon the stoichiometry. Now, look into the properties. Depending upon the stoichiometry, they have different properties, and they remain amorphous up to temperature less than 13 to 15 degrees centigrade. It's amorphous up to temperature less than equal to 1350 degrees centigrade in inner atmosphere. In air, they are stable up to 1500 degrees centigrade. they are they undergo creep hardening after long term deformation. At 1000 degrees centigrade and 1300 degree centigrade in nitrogen atmosphere without vitrification for polysirazine. Now, outgassing of hydrogen and hydrocarbons during
बहुत ज्यादा खर्चा हो रहा है शादी का और कर
outgassing of hydrogen and hydrocarbons during polymer to ceramic transformation leads to difficulties in preparation of these bulk ceramics. Leads to difficulties so for the techniques that are used are cooled isotactic pressing, and subsequent pyrolysis. Of green compact actually leads to causes results in amorphous Hessian bulk ceramics. With a noticeable open porosity of less than 10 volume, with porosity being developed. So at around 500 to 1000 degrees centigrade, this polymer that we started with it transforms into an amorphous assassin which is crack free. Now, talking about the films, assassin can be also deposited in the form of film. Now, the high performance. So now we're talking about assassin films or thin films or coatings, whatever. So the high performance assassin film is due to the small grain size. Then it is a large volume fraction of the interface. The third one is compressive residual stress and growth orientation. And this assassin have shown stability up to 1600 degree centigrade. Now this high thermal, chemical and mechanical stability is due to the large grain boundaries and oxide type of secondary phase in these coatings. Oxide type of secondary phase in these coatings. Apart from that, they also have
बाबा सबसे अच्छा और कम झिकझिक में पर्सनल लोन कहाँ मिलेगा?
बेटा तुम्हारा सिविल स्कोर अगर
they have also low ductility and good thermal shock resistance. That makes them applicable in aerospace, wear oxidation resistance applications, wear and oxidation resistance applications. The carbon and the nitrogen incorporated in the ternary nanocomposite, they play a vital role in enhancing their performance. Have vital role in enhancing the performance. So talking about the applications, they have got applications in turbine engines, blades, wear resistance coatings, in automotive industry, they enhance the life as well as the performance of the components. The other properties of SICN are SICN has got a wide band gap, wide and tunable band gap, which has it has got some optoelectronic properties as well. And they also have good optical transmittance properties. In the UV and IR region, and they lead to its membrane applications. The structure and property of SICN is analogous to beta carbon nitride. And as I previously told, the modulus of beta carbon nitride is even more than diamond. However, it has been found theoretically there is still experimental evidence which needs to be established in this case. SICN
अब आप एक्सेल का काम आसानी से अपने
SICN also has got large cohesive energy. And it has also got it is good hard material for technological applications. So good hard material for technological applications. Now we can make a silicon carbon nitride coating by various physical vapor deposition techniques. The advantage of these physical vapor deposition techniques is it has got a low growth temperature. Chemical vapor deposition techniques can also be used where the temperature is less than 900 degrees centigrade, but it has got a little bit of limitations, especially in industry. Now it has been found that essential films have been grown on steel substrates. And the density of the films is found to be higher for lower values of nitrogen flow. Now, why this nitrogen flow is important? Because of the fact that usually what we do, we make a silicon carbide target, a ceramic target with sintered target is made, and this silicon carbide target is then bombarded with is kept in a chamber and evacuated chamber, and we first allow argon gas to be introduced into the chamber. We ionize argon gas and we allow the argon gas to hit the ionized argon gas to hit the target, and then we also allow nitrogen gas. So the in case of sputtering, and this is where the substrate is kept, so air atoms coming on from the substrate, they ultimately get deposited onto the substrate and we have got a film. Now what has been found is that previously to lower values of nitrogen flow, so lower nitrogen flow, it leads to a denser film. This is one of the observations. And the decrease in density of the film with nitrogen flow is due to the higher pressure during deposition caused by negative DC bias. Due to higher pressure during deposition, caused by a negative DC bias. Now, what is this negative DC bias? We need to clean the substrate, right? So that is why we to make the argon atoms are positively charged. To enhance the flow of argon hitting the target, we put a negative bias here so that the enhancement is, or the striking of the argon atoms is more efficient. So due to this negative DC bias, the nitrogen, there is a higher pressure during deposition, and it has caused the lower denser films to do lower nitrogen flow. That means that the lower is the nitrogen flow, the less dense the film will be. The average hardness and modulus of the certain coatings were 21 gigapascal. This is for the hardness, and 200 gigapascal. This is for the modulus. It's an average value, but there may be slight alterations. And these values were obtained by nano indentation. This is specifically used for film property, mechanical property determination. Now,
अब आप एक्सेल का काम आसानी से अपने फोन से कर सकते हैं।
now the standard deviations of nano indentation experiments, they increase with increase in nitrogen flow. They increase with increase of nitrogen flow. And also there has been an increase in porosity. With nitrogen flow. Apart from films, there has been also SiCN cones which were synthesized on silicon wafers with gas mixtures, different gas mixtures. So these gas mixtures were methane, CH4, SiH4, argon, hydrogen, nitrogen. Now cones, these cones are basically nanometer sized tips and a higher substrate temperature facilitates crystallization at larger crystalline size. So if we increase the substrate temperature, it leads to crystallinity. That means a larger crystal size. X-ray photoelectron spectroscopy. This is just something about X-ray. Photoelectron spectroscopy. Was used to find out the bonding structure and the composition of the film, or the bonding structure and the composition of the film, and it has been found that these two parameters they can be manipulated, tuned rather, through varying the nitrogen flow rate, by varying the nitrogen flow rate. Now, if you use a single source precursor, for example, so precursor means starting material. If you use single source precursors, for example, if you're using material CH3 2 H Si NH N CH3 2, and if we do SNFT studies, so we find that the bonds like CN or SIN, they are mainly peculiar to the film synthesized in the system with excited helium. These bonds play a vital role. Now, chemical bonding, atomic local order in the amorphous matrix, they get complicated than those of Si3 and 4. So, if we look into the chemical bonding or the atomic local order, of the amorphous matrix, why it is being called a matrix is because of the fact that when we are depositing an SiCN film, a nanocomposite SiCN film, it's basically and an amorphous matrix, first of all, of SiCN. It is an amorphous matrix of SiCN, and in these matrix, small crystallites of different phases, they start to develop based upon the what temperature we have used, what is the pressure we have used, what is the negative bias that we have used, or let us B. So and power also. So the deposition parameters will determine what kind of phases will be developed. Now the chemical bond and the atomic local order of amorphous matrix, these are quite complicated if we compare to that of Si3 and 4. If we take the phases individually, C3 and 4, so the chemical order in the amorphous matrix is quite complicated, and the optical band gap, as we have seen, that SiCN has got the optical band gap of SiCN has been found to be between 2 and 4.7 electron volts. These materials have been found to highly resistant to thermal degradation, as we previously told. And it has also got something called a moisture resistance. And is mainly influenced by the stresses in the film. And the best results of these exhibiting properties of best results are obtained when we have no compressive stresses in the film. This actually leads to the best film properties. Now, with rising argon concentration in the gas mixture, the silicon content in the film rapidly increases, whereas carbon decreases the nitrogen concentration. So, the feature is that if the argon concentration is increased in the gas mixture, it leads to silicon content increasing, and whereas the carbon concentration it decreases, nitrogen and carbon concentration it decreases. As infinitesimal bombardment of growing film by argon leads to its supplantation into the films and to decrease in volume concentration of hydrogen, so it may so happen that this argon, when being bombarded into the target, that gets implanted sometimes. This can also happen. And also the volume concentration of hydrogen, if you're using a precursor, it also decreases. So these are the properties that is happening. So due to these properties of increasing hydrogen concentration, the nitrogen silicon bond on the silicon nitrogen bond, whatever you may call it, they dominate over the respective, so these becomes dominant. Over other bonds like nitrogen carbon bonds and silicon oxygen bonds. And they are preferred in a pure nitrogen discharge, and the film hardness increases up to 40 GPa. So this will cause increase of film hardness to 40 GPa. Possible to change the, if you change the nitrogen argon ratio, with various compositions of Si, Cx and Y films, leads to various compositions of SiCN. So in that case we will call them Si, Cx and Y films. during sputtering by various nitrogen content in the gas flow mixture. The Young's modulus E. The Young's modulus decreases with carbon content of the film. Modulus goes down as carbon content in the film increases, and the formation of C triple bond C, C double bond N, and also C triple bond N. These bonds are together with the occurrence of terminating nitrogen. Occurrence of terminating nitrogen atoms for the film with higher carbon concentration. With higher carbon concentration. So carbon concentration is causing a decrease in modulus and formation of these bands and all the terminates in nitrogen. Now, as far as the phases are concerned,
बाबा सबसे अच्छा और कम झिकझिक में पर्सनल लोन कहाँ मिलेगा?
बेटा तुम
SiCN, as previously told, it leads to formation of Si3 and 4, C3 and 4, and silicon carbide phases on the amorphous SiCN matrix. Now, the beta C3 and 4 and beta SiCN 4, these two have the same structure. So these two have the same structure. They might be expected to be mutually miscible, so expected to be mutually miscible. Giving rise to silicon carbide, which has got a potential industrial application. So this mutual miscibility leads to formation of silicon carbide, which has got industrial applications. Now, nitrogen, a fraction in the gas mixture has major influence on the deposition rate. So deposition, nitrogen flow has got, it affects the deposition rate and composition of the films, and also in higher nitrogen concentration and nitrogen fraction for that matter, it will result in increased deposition rate and also ratios. So what we can find is that the SiCN films are mainly amorphous in nature. The existence of SIC CN single and double bonds. So let's put it in this way. You have SIC bond, we have CN bonds, and also C3N bonds, and also SIN bonds in the films.